Good morning, ladies and gentlemen. We're going to go through lesson 5, prefix sums, and do some of the Codility developer training tests here. The first example is passing cars, which is labeled easy. And we're just going to go through the reading material to have the overview of prefix sums and see how we can apply it to these examples. So here I have the reading material, and you can see the general formula for the definition of the prefix sums function. It's just basically a running total. So if we have an array A of n elements, we're basically getting length of the array A, and getting the prefix sums to, and we append basically the shell of it, so 0 times n plus 1, and for every range of k, we are just adding a running total. So we're just saying that whatever that last element, k minus 1 of A, of the array A, we're adding it to the prefix. You're prefixing a sum at the end of array P. So imagine you're at a concert and want to keep track of how many people have entered the venue so far. The regular way is that to calculate is that every time someone enters, you count all the people inside. This takes longer as more people enter. So a prefix sum is supposed to reduce the time complexity, right? If every time someone enters, you want to count all the people inside, it takes longer as more people enter, right? What a prefix sum does is you keep a running total. So when the first person enters, the total is 1. When the second enters, the total is 2, 1 plus 1. When the third enters, the total is 3, 1 plus 1 plus 1, and so on. Now, if you want to know how many people entered between the 10th and 20th minute, this is where prefix sums come in, because there's a second dimension here where we consider time, right? And the regular ways, you'd have to count everyone in the venue at the 20th minute. So basically, we are calculating the running total of 20th minute by running through the entire array at the position 20th minute, then count everyone in the venue at the 9th minute and subtract. So that's a quadratic time complexity, O(n) squared. Lots of counting. Now, the prefix sum way is you just subtract the total number of people at the 9th minute from the total number of people at the 20th minute, much faster. And that's what we call O(n) time, or linear time. And every operation is just O(1). So it's constant operationals, right? Just one operation per execution. Now, which is basically just one loop. So prefix sums are like that running total. They make it super quick to find the sum of a bunch of numbers within a range. In simpler terms, right, imagine a stack of books. Prefix sum is like keeping track of the total height of the stack as you add more books. To find the height of a section of books, you just subtract the height of the stack before you added that section. So that's cool, because prefix sums are a clever trick that can save you a lot of time when dealing with numbers. I want to run down into this example here where it looks very complex if you start reading the kind of introduction to this example of the mushroom picker. And I want to summarize basically what this means, right? In terms of what is this, right? Visually, we imagine a road with mushroom patches. You're a mushroom picker, okay, standing at a certain spot. You can only move one spot at a time. So that's what this is. We know the mushroom picker is at spot number K on the road and should perform M moves. So what do we know? Here's the problem. We have a list showing how many mushrooms grow on each spot along the road. So if you look at this is a spot along the road, right? The length of this is n plus 1, 6 plus 1. So we have 7 positions. Here, indexed by 0, 1, 2, 3, 4, 5, 6. They represent spots on the road with the elements representing the number of mushrooms. So on spot 0, we have 2 mushrooms. Spot number 1 on the road, we have 3 mushrooms. Spot number 2, 7. and so on. To spot number 6, we have 9 mushrooms. So you know your starting spot. You know how many moves you can make, which is k equals 4. Starting spot circled 4, and you should perform m moves, 6 in this case. You need to figure out the best way to move left or right to collect the most mushrooms. So why this is tricky is actually, if it's very tricky if it comes out in the exam or any exam related to codility testing, but in this case, our example here wouldn't be that difficult since this is an easier one. This is a much harder example. It's tricky because you could move back and forth, and that might not be the best way. You need to find the most efficient path to collect the most mushrooms within your move limit. So you can simplify the solution with an assumption. So there are assumptions to the most efficient way to do this, right? But the prefix sums part is to imagine you calculate the total number of mushrooms from the beginning of the road up to each spot. If you have prefix sums, this assumption means that it would reduce your time complexity. This is like keeping a running total, right? Just anytime you hear about prefix sums, don't care about the calculation. Think just about a running total. P is the running total, right? So the assumption is that we want one direction, then maybe back. So the best strategy is usually, in these kind of cases, is to move in one direction, left or right, for a while, and then maybe turn around and move back a bit. So one adjustment for every 6 moves, depending which permutation of the 6, which direction you start left, you have to go and move to right. Start right, goes and moves to left. And so, if you move right, you're moving right for 0 moves, then left for the rest. Right, moving 1 move, then left the rest, so on. That's the kind of loop iteration you're going to have. Move left first, assume moving left, then you move left for 0 moves, and right for the rest. So that's k minus p, or in this formula, for example, we have left position, k minus p is the number of left positions. So if p is 0, then right, of course, is 6, which is the min of n minus 1, and we take this also minus 2p because you have to reverse the positions of the move to the left. Sometimes the range is dependent on the right and left boundaries, and this is this formula you get. It takes a while to get through this formula, but I won't have the time to sort of break it down. To just know that this works as a key point for a mushroom for the efficient algorithm in O(n plus m) linear time. And the example for, hold on a second. All right. If we're to have O(n squared complexity or O(m squared complexity, the best strategy is to move one direction optimally followed by some moves in the opposite direction. Notice that this strategy, they don't use prefix sums because prefix sums limits the search space. And this is another important point I want to bring up. It limits the search space. If you have 2 dimensions, iterate through array I, then for every array I, iterate through array j, you're basically doing a vector sum approach. So you don't want to get the difference from every single standpoint. You want to have a range from a single iteration. So from a single operation that does it all at once. So with the fact that if there's no prefix sum for this, we just take the moves left and then moves right, no matter the boundary. So you can just do this and then whatever, and you calculate each running total. You can't just minus whatever is right from left in order to get the most efficient sum total, because you're going to have to keep adding positions and extra mushrooms, which is not that efficient. So that sums it up. Now let's go to the lesson before we run out of time. This is a bit hard to explain, but we did it. I could explain even further if there are any questions there. You can always go deep dive into that mushroom picker example. That was a very difficult example, but let's go quickly and read this exercise and try to execute this one. So in this case, this is another what we call the passing car problem. As you can see from the title, it's labeled passing cars. Okay. So a non-empty array A consisting of n integers given the consecutive elements of array A represent consecutive cars on a road. Array A contains only zeros and or ones. 0 represents a car traveling east, 1 represents a car traveling west. The goal is to count passing cars. We say that a pair of cars, PQ, where PQ is a range of n, is passing when P is traveling to the east and Q is traveling to the west. For example, consider array A such that A0, so at position 0 of the road, taking this to the leftmost part of the road, we've got 0, which is, what's that? Represents a car traveling east. 1 traveling west. East, west, east, west. So these are all positions on the road where the cars are traveling in a certain position. We have 5 pairs of passing cars. And it's a bit hard to read, but we can see. And the logic is here. Taking 0, which is the first 0 indexed one to the leftmost car of the car going east. 1, right, is showing that on index 1, on index 0 and 1 is the first passing car going west. And then we have 3, which on index 3 is another passing car going past this initial car that's going eastbound on index 0. And we got 0, 4 as well. And then we go to the second eastbound car on the index 2, and we see that we don't calculate the one here on the westbound, but we do have 3 and 4. So 2, 3, 2, 4, another passing car. So we have to write a function that given a non-empty array A of n integers, it returns the number of pairs of passing cars. Function should return -1 if the number of pairs of passing cars exceeds 1 billion. So we're going to with the example given, it should be 5, right? Why is that? Because we have 5 pairs of passing cars. And we use the eastbound and westbound examples. But this problem, again, if you spot properly, that this is calculating using an ON squared time complexity, because it's using for every eastbound car, we're recalculating for every loop of the time. We have to loop through this to find the eastbound car. Once we find 0, and then we loop it again. So it's a multiplicative, right? It's n times n, because the number of iterations we have to go through the loop to find the eastbound car, and then once we found one, we have to go through the loop again to find every westbound car that passes the original indexed eastbound car. Then we go to the next eastbound car and then find every single westbound car after that passes this eastbound car, and we have a running total. But it is not the efficient prefix sum formula. The prefix sum formula would assume that we simply add a prefix sum p running total, and then we subtract the differences between each time a car has passed the original, right? But actually there's a much easier way. Instead of using the regular prefix sum, we can also use an example or mock-up, kind of trick around the prefix sum, and I'll show you later how it's done. So I hope that I explained this well enough, this part of the passing cars problem. It can be a little bit too hard to explain, but and there are a couple of ways to explain or to sort of solve this problem. And like I said, rather than doing n time complexity to iterate through every single to doing n times n, iterate through every single east car, and then iterate through every east car for every west car clashing with that original east car. So let's come out with an example that would help us with this particular problem. So let's start this test. I think we are ready. I want to do it in Python, so I'm just going to confirm, and we'll type a solution. Now, for every solution, it's very important to write a documentation to explain, essentially what we're doing, instead of running into rabbit holes where we already got our assumptions wrong because we have a lot of assumptions when we're reading the question. We didn't think through the solution, and we are running through rabbit holes trying to force a solution out from assumption. That's a very bad approach. We don't want to force solutions out of assumptions. We want to clarify our assumptions in order to have foolproof solutions. Not really about solutions, but questioning assumptions. Because as long as assumptions are right, the solution is always going to be right. And there are multiple solutions given the correct assumptions. Given the wrong assumptions, however, there's an insoluble solution that basically caught between a rock and a hard place. A lot of these rabbit holes could be come out of if we had good reasoning, or even good documentation of our reasoning behind how we think as programmers. So what we want to write, for example, for solution A is count the number, and what this one we should count the number, and we can see that this is obvious because it says the goal is to count passing cars. So if the goal is to count passing cars, I want to say it counts the number of passing cars, right? That's my first. Anytime I have a test, I want to, make sure that I get the goal of the thing and succinctly say it counts the number of passing cars, all right? So we got args. The next section of the functional documentation of functions is to put what the arguments are. Args and A, I can say A. Sorry, 1 second. Just moving my computer a bit. All right. A non-empty array of zeros and ones, where 0 represents a car traveling east, right? So it says here, it represents a car traveling east, and 1 represents a car traveling west. Right. Okay. I'm moving the mic a bit. All right. Traveling west. All right. And what does it return? Returns. Oh, mic is in a different position. All right. It returns the number of pairs of passing cars, or -1. So I didn't. So sorry. What am I doing? I don't know what I did there. All right. So I'm trying to remember all the edge cases as well. So remember this one. Return -1 if the number of pairs exceeding cars. Right. So -1. We can just copy this actually. Or -1 if the number of passing cars exceeds 1 billion. So there we got very nice returns because it tells us what exactly we're returning in terms of function, and we close it in triple quotation marks. Essentially, what I plan to do instead, like I said earlier, okay, instead of looping through the entirety of zeros and ones, and for each 0, or doing the other way around, doesn't matter. That means for each AI, I'll calculate an ij, right? Which is basically an n squared time complexity. Instead of that, what we want to do is instead of 1, 2 is where we focus on just the eastbound cars. which means we don't need to calculate 2 loops. We just calculate 1 loop. And how do we do this? We can have a counter for eastbound. So the idea is that for every eastbound car, I have a running total. For every eastbound car, I'm just adding the westbound cars that pass eastbound cars and then incrementing totals of every eastbound car with every westbound car as a running total. I'm not recalculating the entire loop. And you see how this works. I first have my eastbound car, which is like my prefix sum. So I have my eastbound cars. Notice what I'm doing, right? I am not saying that I'm using the prefix sum formula as we've seen in this PDF, right? I'm not using this formula here, right? I'm not using this formula here, but I hope you can see that even though I'm not using this formula, right? This little whimsical formula, very whimsical, but you know, it's I can basically set a variable that acts like a prefix sum. If I have a counter eastbound cars equals 0 and I only count the passing cars, notice I don't have westbound cars. Now you could have also a counter for westbound cars, you know, let's say, oh, westbound cars, you can just initiate a counter like that, let's say, and you know, we can also have AI, if AI, you know, I think I pasted this somewhere, this solution, but anyway, it doesn't matter. So if AI, for example, and then we loop it with an AJ, where it's A, you know, I, okay, so basically the logic goes like this, right? Passing cars equals 0 and we got n equals then A, let's say. In this solution, we can say what, for I in range n, this is a traditional example, right? And we'll have the O(n) squared example, as we can see, if if AI is equals 0, if the current car is traveling east, essentially, there's a simple solution. Well, it seems simple, but then we have to say for j in range. And this time we say range I plus 1, right? N. Because now we're saying for every west car, we calculate this. So this is an original, right, O(n) squared calculation. I'm just trying to show you what this is. But instead, we can just don't have the westbound cars and just keep a running total of eastbound cars and every westbound cars that passes. And I'll show you how to do this, right? Essentially, this is what goes on in my head for I in range. And this is a simple trick, see, for the loop that we have here for I in range. We don't have to put n, but we can in terms of just proprietary in terms of this code, right? Because it says n in the codility test, so we can say n is length a and say, you know, for I in range n. And we do the same thing, but instead of looping through it, we just say, we loop it once, right? If AI equals 0, eastbound cars, that's common sense, right? Eastbound cars, obviously, we increment that by 1. And then we've got an else. We would say, well, in that case, else, and this obviously is talking about now the, if it's a westbound car, which I'm just putting it in this example to show you what exactly is the logic here happening, right? If it's a westbound car, then we immediately put into passing cars, and this is our prefix sum. Sorry, actually the prefix sum was not eastbound cars, this is just the indicator. But in terms of westbound, I don't have to keep running total at westbound because I'm adding the number of eastbound cars that the passing car, so whatever is this westbound car, I'm just adding a number of eastbound cars. How does this work? Interesting. Now we can see here we've got a perfect running prefix sum, because for every passing car to eastbound cars, we have the running total of whatever this eastbound car represents. Now, if we iterate through the next one, we have a running total of the eastbound cars. Unlike our previous example where we don't have running totals, we have every single westbound car and every single eastbound car clashing and calculating the sums of every single possibility. We are simply saying let's calculate these possibilities, whatever range it is, because we can have a lot of n integers and we still have better simplicity with this, because it's simply a running total. We got eastbound cars plus 1, passing cars for every passing car, right? If it's a westbound car, then we say, look, there's 1 passing car, and we're using the same number from the eastbound cars. Of course, it's just a say that increment 1, and whatever eastbound cars there is for whatever westbound car is coming in for, if it's not a 0, it has to be a 1, right? In this case, if it's westbound car, meaning that if a, or I mean in this case I would say if ai equals 1, right? So obviously then it will be just considering what is required. Passing cars is a prefix sum. It's saying P, whatever's in P, adding to the last iteration of the last value of eastbound cars, a lot of memory is saved. So, and whatever comes next, it could be just another 2 eastbound cars or 3 eastbound cars. Whatever west car is coming, it's going to pass 3 eastbound cars. Whatever next westbound car, it doesn't matter what it is, it's going to pass 4 eastbound cars. No matter what the calculation, it's a running total. So that's the idea. And then we can put our edge case here. If passing cars is more than 1 billion, you're not supposed to put 1 to the power of 9, but this would be 2. Hopefully there's enough zeros there. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Return -1. And of course, you want to finish our function here with return passing cars. And there you have it, passing cars. Let's see if this is correct. We're going to go to the next example. Hopefully you understand a little bit of prefix sums now. And the next example, we're going to the next coding test, which hopefully you would have a better clue on how to do. Thank you very much. Have fun.